We've talked about angles in standard position, which is what we're talking about when we introduce the unit circle. So there are a few things that we need to go over though before we hit the unit circle. Remember how sine of a number, an angle I mean, is opposite over hypotenuse. Well, if I look at an angle in standard position, here's my angle theta, I know that this is the opposite and this is the hypotenuse. And we see that the opposite is actually the y value of this coordinate. Remember, this coordinate is x comma y. And the adjacent, by the way, is the x of that coordinate up there. And the hypotenuse we'll call r, but it's the distance, Pythagorean theorem, all that good stuff. So if we look at opposite over hypotenuse, it ends up being y over r. And if I say the cosine of theta, cosine SOHCAHTOA is adjacent over hypotenuse. Well, again, look at my angle in standard position and look at adjacent over hypotenuse. The adjacent is the x of that point, and the r is, they call it the radius of rotation, r. R is the hypotenuse, x over r. And the tangent of theta, tangent is opposite over adjacent, and opposite is the y, right there, and adjacent is the x. Now this is huge. It helps us understand the unit circle. I'm not going to be using this too much as I talk about the unit circle. Sine, opposite of hypotenuse, is y over r. Sine is y over r. Cosine is x over r. And tangent is y over x. You have to memorize these. You must know them to function. So here you see the unit circle. And what I want you to observe is these numbers here. This seems like all a mystery. Where the heck are these things coming from? Well, it actually isn't a mystery at all. So I'm going to show you where those things come from. So we'll shrink this thing down and get it out of the way here for a moment. And go back to our angle in standard position. So let's remember our special right triangles. Remember, I've been emphasizing these, saying how important they are. And let's take a 30-degree special right triangle in standard position. So this distance here is, remember, between the 30 and the 90, the root 3. Between the 90 and the 60 is the 1. And the hypotenuse is 2. What makes the unit circle special is the word unit means 1. So, in fact, what we're going to do with the unit circle is call this length 1 every single time in the unit circle. And as I go around, that 1 is the r, it's the radius of rotation. As I go around my angles in standard position, r is always going to be 1 every time. Well, you might remember from geometry, and we've done this before too, we used to call this t root 3, this t, and this ended up being 2t. So if I solve, I see that that's always going to be 1, and that 2t is equal to 1. T is 1/2. So this length here is 1/2 root 3, or we could say root 3 over 2. That is the x. And this length, remember t is a half, ends up being a half. And so that is the y of a half. All that work I just did was a little bit extra because observe that if this is 1 in the unit circle, then basically look at the 1 and the 2, every side is just half. So the 2 ends up being halved, become 1. The root 3 ends up being halved to become root 3 over 2. And the 1 becomes halved to become 1/2. And this point then, the point at the end in standard position is the x and the y. It's root 3 over 2 and 1/2. And now we go back to that unit circle. So let's bring it up here and make some observations. And take a look at the unit circle. And notice the first coordinates at pi over 6, which is 30 degrees, is root 3 over 2 and 1/2. That's where it comes from. I'll do one more to help you understand. So let's say that we had a 45-degree angle in standard position. So that this was a 45, 45, 90. Well, the sides of a 45, 45, 90 are 1, 1, and root 2. But remember, in the unit circle, this has got to be 1. So let's go back to our t, and t root 2. And these two have to be equal. T root 2 has got to be 1. What would my t be? What would be those lengths? What would the 1 and the 1 become? So I'll divide by root 2, divide by root 2, and rationalize. I see that t is root 2 over 2. So if our root 2 hypotenuse is 1, like it's supposed to be in the unit circle, then these two lengths right here and right here, the 1 and the 1, they're actually the t, they're both root 2 over root 2. So let's replace those with root 2 over root 2, root 2 over 2, and root 2 over 2. And then let's look at this point. This point consists of an x and a y. The x is right here. It's root 2 over 2. And the y is right here. It's also root 2 over 2. And then we'll bring back that unit circle. And notice that at 45 degrees, what the coordinates are. Root 2 over 2 and root 2 over 2. So I can do the same thing again with a reference angle of 60 degrees and use the 30, 60, 90 and label the sides. Remember the hypotenuse is 1 and find the lengths for x and y, and they will be 1/2 and root 3. Now here's the key part. So you see where these numbers came from. They just come from the special right triangles. But notice how they repeat as you go around the unit circle. The reason they repeat, this is the key to understanding, is that everything is based on a reference angle once I get past 90 degrees. The reference angle is always between the x-axis and the terminal side. So right here, the reference angle is 60, and I'm using the same exact triangle if I was over on the other side. There's my reference angle, and there on the other side in quadrant 1 is the 60. It's the same x and y values, but the difference is going this direction, x is negative. Notice the negative 1/2. So the same thing occurs over here at 45 degrees. Because it's the same exact reference angle as the 45, 45, 90, but again, going that direction, x is negative. So the x coordinate is negative. And if I go to the 30, 60, 90, the 30, 60, 90, over here, there were the lengths that made the x, remember the radius was 1. As you go around, the radius of rotation there, that this was 1/2 and this was √3/2. We just did that a bit ago. That it's exactly the same triangle over here based on the reference angle, and this is negative √3/2 because it's on the left side of the origin for x, and the radius is always positive, it's always 1, and the y is positive up here, it's 1/2. And if I continue on around, the same thing happens. So down here, this is a reference angle of 30 degrees. And when I make my triangle, this length is negative √3/2, and it's negative because it's going in to the left of the origin. And going down, it's the same, again, it's the reference angle, it's the same 1/2, but it's negative because you're down in quadrant 3. And if I go over here in quadrant 4 and look at this, there's my reference angle of 30 degrees. This is still negative, it's negative 1/2, the same lengths in the 30, 60, 90. The r is always 1, but the x is positive. This length here is the √3/2. So these things repeat as you go around because everything is based on the reference angle, and the only thing that changes is the signs. So that's where the thing I showed you at the very beginning comes into play. When I say sine, remember, it's opposite over hypotenuse, but I just told you that the sine of an angle in the unit circle is y/r. Remember that r is 1. So I can look here at 30 degrees and notice that y is right here. Y is 1/2 over 1, which is 1/2. So the sine of pi/6, or 30 degrees, is 1/2. The cosine of pi/6, well, it's x over r. R is 1, so that you divide by 1, nothing happens. So again, it's just right there. It's x. It's √3/2. The tangent of theta, any angle, is y/x. So when I have to do a little work with tangent. When I say the tangent of pi/6, well, it's y/x, and I'll put the y up top, which is 1/2. I'll put the x below, which is √3/2, and I'll multiply by the reciprocal. Since I'm dividing, I'll flip that bottom fraction. Notice how the 2's cancel, and I get 1 over √3, and then I have to rationalize, and I get √3 over √9, but the square root of 9 is 3, √3/3. So it's just as simple as understanding that the sign in the unit circle is y. It's y/r, but it's y. So you grab the y coordinate for sine. The x coordinate for cosine. Just look at the x coordinate and you have the cosine. Tangent is the one you got to do a little bit of work with. It's y/x, so you've got to multiply by the reciprocal and simplify, and that's why we got √3/3. A few more examples, just so you can see how easy this makes things. If I ask you for the sine of 3 pi/4, sine is y/r, which is of course y/1. And so all I do is I go to 3 pi over 4, and I look at the coordinate, and sine is y, but remember it's over 1. Anything divided by 1 is itself. It's just root 2 over 2. If I asked you for the cosine of 7 pi over 6 radians, I'll go right here to 7 pi over 6. And cosine is x over r. And again, r is 1. So it's just, let's go find the x here. It's negative root 3 over 2. And we're done. If I asked you for the sine of 5 pi over 3, well, sine is y over r. Again, r is 1, so I don't need to worry about that. I just look at 5 pi over 3 right there, and sine is y, so it's negative root 3 over 2. If I asked you for the cosine of 11 pi over 6, cosine is x over r, and x right here is root 3 over 2. And we're done. The one that takes a little bit of work is the tangent. With tangent, we have to divide y by x. So the tangent of, let's do 2 pi over 3. We go to 2 pi over 3. 2 pi over 3 is, I'll change colors here, is right there. And we're looking at this coordinate. Not a very good arrow there. And it's y over x. So we take the y, which is root 3 over 2, and we divide it by the x, which is negative 1/2. Now I'm going to shortcut this a little bit. It's root 3 over 2 times, I'm going to multiply by the reciprocal and flip that, negative 2 over negative 1. The 2's cancel, and this ends up being negative root 3. So in the unit circle, we use sine is y over r, cosine x over r, tangent y over x, and we can just look at the coordinates because r is always 1, and we can just simply use the coordinates to immediately find the sine, cosine, and tangent of any of those angles.